everyone. So what you have to know about me, that I like to collect security certificates, and I'm also really into offensive research. For example, I have developed the zombie browser toolkit some years ago, which you can use to attack browsers. I'm also the developer of the hardware firewall bypass tool, which you can use to circumvent hardware firewalls in special offensive attacks. I'm also the developer of the malware analysis sandbox tester tool. So whenever you are on an engagement where you have to bypass a malware analysis sandbox, you can just use my tool to fingerprint the malware analysis sandbox, and based on the fingerprint you can create a new malware sample which you can use to bypass it. And last but not least, I also played a little bit with crappy IoT devices. So what I'm going to talk about today, I will have a quick introduction about elliptic curve Diffie-Hellman encryption and how it connects to my Iron Squirrel project. I will talk about the attacker model, who is my attacker in this project, why I believe that this topic is different and new. I will talk about some defense and offense, this cat and mouse game which I really enjoy. Let's start. So how did this whole story begin? I think behind every research and offensive research there is a story, and usually my story for every offensive research starts like that. A vendor says something that they can detect this, or they can prevent it against this kind of attack, and I tell them that I'm pretty sure that I can find ways to bypass it, and they say, oh no, that's impossible. And whenever someone says me that it's impossible, I'm really pissed up, and I go home and I start to code. I think all of my offensive researches started somehow like this. Okay, so why you should listen to my talk? If you are an exploit broker or work in law enforcement, hands up. No? So, but if you are, then I'm going to show you a way how you can prevent your zero-day exploits being leaked. How many of you guys penetration testers, red team members? All right. For you guys, I can show you some ways how you can bypass perimeter defenses. If you are in a blue team member doing forensics investigations or just research exploit kits. All right. So I'm going to show you how your current defenses can be bypassed with a tool like my Iron Squirrel attack tool, and what you should look for when you do forensics investigation. And if you are in none of these topics, then maybe learning about elliptic curve cryptography can be fun. So let's start with the introduction. I'm going to talk about exploit kits and 0 days. I will talk about Diffie-Hellman key agreement, elliptic curve Diffie-Hellman key agreement, and my encrypted browser exploit delivery, and how my idea was implemented by the bad guys. So what is an exploit kit? An exploit kit is a software which exploits other software, mainly a browser. Pretty easy. But what happens if you have a 0-day exploit and you lose your 0-day exploit? I'm giving you two stories from the recent past. First of all, there was this targeting of Ahmed Mansour with an iOS Safari 0-day exploit. I'm not sure if you remember this story, but what happened that Mansour received a link on his iPhone. He didn't click the link because he knew that this is an attack, so he forwarded the link to some researchers. The researchers bought a new iPhone. They did set up an analysis environment, clicked on the link, they grabbed the whole network traffic, and they identified that there was an iOS 0-day in the network, so they have sent the PCAP files to Apple, and basically this 0-day was discovered, and the iPhone was patched. By the time this exploit happened, one iOS 0-day like this cost like 100,000 US dollars, or maybe $1.5 million US dollars, based on who do you ask. So it's a pretty lot of money to lose. And unfortunately, even though this 0-day was not effective against Mansour, because he found out that he's being targeted, he's imprisoned, and he's still in prison, unfortunately. The other interesting example, when law enforcement in the USA, they targeted pedophile site, and they basically took control of this pedophile site, and they implemented a Tor browser 0-day on the site. So all the visitors who visited the website were their browser was exploited, and whenever the attacker code was able to run, their original IP address was leaked. By the time of this attack, Tor browser 0-day was something like 40,000 US dollars. So as we can see, if you have a browser 0-day, but you lose it, you lose a lot of money. So how many of you guys know about Diffie-Hellman key agreement? All right, quite a lot. I have found this example, how you can imagine how Diffie-Hellman works on Wikipedia, and I like it very much. So let's say we have Alice and Bob, and they want to agree on a shared secret, but they have to communicate over a public communication channel. And let's say that they have agreed that they are working in a system where yellow is a common paint. And they both choose their secret color. Alice is choosing orange, and Bob is choosing some green something. And they will mix their secret color with the yellow common paint at home. And they will get this mixture colors. Now they can use the public transportation and send these colors to the other. And let's say that there is an attacker who can see what kind of color was transported to the other party, and also assume that mixture separation is an expensive operation. For example, for me, it is very hard because I have no idea how these colors were created from my top of my head. I know that it can be done, but let's just assume that this is a hard problem. Now they both have their secret colors and the color they got from the other party. And now if they mix it, they will reach their common secret, which is something like brown in this example. And now they can use this common secret for example, as a shared secret key for communication. In reality, this whole mathematics is based on modulo algorithms. When you choose how huge basically your clock is and what is your first starting position, then you start to multiply it by itself, and you are basically jumping around the clock. When it's small, it's easy to calculate how you got there in the end position, but whenever we are talking about very huge clocks, it's basically impossible to know how you got there without trying all the possible combinations. So it's a hard problem. The difference of elliptic curve-based Diffie-Hellman is that it's a lot faster, especially the key agreement part of the protocol. And it will be important in my presentation later that, for example, Diffie-Hellman key agreement implemented in JavaScript is too slow for nowadays. And how elliptic curve-based Diffie-Hellman really works, Unfortunately, 45-minute presentation won't be enough just to explain it, how it works. But basically, you have to think about that there is this commonly known curve, which is the red one, which everyone knows. And we implement some new mathematical formulas on this curve. And it's basically looks like ball bouncing back and forth on this curve. And it has the same property as the Diffie-Hellman, meaning that it is very easy to calculate it one way, but it is very hard to determine how we get there. It's basically very similar to the billiard ball on the billiard pool table. So if you know that you start here and you use some amount of force in that direction, you can calculate where the ball will end up. But if you know the end position of the billiard ball, it is very hard to say that this ball got here with this amount of force this way. It's pretty hard. So now that all you know the cryptography behind my project, let's deep dive into how this really works. So let's say that the client browser is initiating a new connection to my web server, which is the attacker server. For example, he wants to visit a website, look at cat pictures or whatever. In the second step, the server generates the elliptic curve Diffie-Hellman key parameters, and it generates its own secret key. So in the first step, the server can send back the client some crypto libraries in JavaScript, all the common parameters for the elliptic curve Diffie-Hellman encryption. Now it also can send back the elliptic curve Diffie-Hellman public key of the server, because it was just generated right now. And all of this stuff is sent to the client. So in the fourth step, based on the crypto library, the client can generate its own private key, and it can instantly calculate the shared secret key because it already has the public key from the server. Now the client has to send his own public key to the server, and at this point they both know the same shared secret. They can calculate it. So from now on, the server can send back the exploit in an encrypted way, which is encrypted with the key they have just agreed on. And now the browser client can decrypt this exploit in memory and run the exploit code in memory. And this whole protocol has some very nice and interesting features, which I will discuss later, because this way the whole exploit code was encrypted on the wire, and it was decrypted just in the memory. Now, whenever you run code on the client, usually what you do is that you initiate a download of a malware from a server, and you start it. In my code, what I have implemented is that even the malware what you download is encrypted. It's again encrypted on the wire, and whenever it's sent to the client can decrypt it and start it. So on the wire, you just see encrypted stuff. Now, I believe that this was very hard to process, so let's show you in some demo how this really works. No, this one. So here I'm using Chrome, and there is no exploit in this. I'm just running some demo JavaScript code here, as you can see. And here you can see some encrypted data, but you cannot see the alert code, which I just shown to you, right? Now let's write that instead of this eval function, let's try to write this code out, and let's see what this does. Before doing that, I'm just showing you that this is what you can see on the wire. So again, there is no alert here. But if I run this, you can see that I was able to decrypt this alert message. And how am I able to do that? Because I purposefully stored the decryption key in the memory. And as long as the decryption key is in the memory, I am able to decrypt the content of it, right? Good. I started this project more than 2 years ago, and my original proof of concept code was done in Node.js. I chose Node.js for 2 reasons. First of all, I have never used Node.js before, and I wanted to play around with it. And it was pretty handy because with Node.js, you can use the same crypto libraries on the client side and the server side. And this is very, very good when you are implementing crypto, that you can use the same language. After a while, I figured that it would be very good to implement this project into Metasploit. And Metasploit is written in Ruby. So let's try to port this project into Ruby. You have to know that for Node.js, it took me like 1 or 2 days to implement this whole functionality. But when I ported it to Ruby, and I had to match the crypto from JavaScript to the crypto to Ruby, it took me basically 1 week to implement it, even though I had more experience with Ruby. But finally it works, and I have tested it with a full lot of different browsers, and I can promise that this whole Iron Squirrel project is compatible with the Edge browser, IE11, Firefox, the Tor browser, Chrome, Opera, Mobile Safari, Mobile Chrome, Android built-in browsers. So basically every modern every modern browser is supported. And by the time when I created my first Node.js proof of concept code, I was pretty happy about it. So I made a blog post of it, and I tweeted about it. And it was a really huge success because I got 3 retweets and 3 likes. That was fine. I mean, I didn't do this for the recognition, but that was fine. And 2 months passed, and I just read on a FireEye paper that attackers started to use Diffie-Hellman encrypted exploit delivery. And I was like, whoa, someone actually read what I just did, and they implemented it. There were some differences how they did that. First of all, they have used plain Diffie-Hellman instead of elliptic curve Diffie-Hellman. And by that time, they didn't use any 0 days, so they were not interested in hiding their exploit code, but rather they have protected the shellcode itself. And I want to believe that this is not a coincidence, that there were exploit kits like for at least 6 years in the wild, and just 2 months after I published my code, they have implemented this. And it turned out that this encrypted shellcode was a real pain for all the AV vendors. And AV vendors were thinking, all right, we are facing encryption problem. So what we can do is that we use math to solve the encryption problem. And turns out the Russians are very good when it comes to math. And Kaspersky Lab started to analyze the implementation of this exploit kit and how they implemented Diffie-Hellman. And turned out that because they couldn't use long keys, because generating long keys take too much time, these short keys were susceptible to factorization. And they published a very nice paper about it, which I tried to understand, but I have no idea how the attack works, but it works, so it's pretty amazing. And I already mentioned that the Angler exploit kit was the first to implement this attack, and after a while Angler disappeared, and but now still there is another in the wide exploit kit which uses this kind of attack, and this is called the Astrom or Stegano exploit kit. So I believe this is what the Angler exploit kit developers were thinking when their shellcode was decrypted, because they had to use old IE browser because they attack vulnerable browsers. Because of this, they couldn't use elliptic curve cryptography, and because of this, their code was basically reverse engineered. All right, now let's talk about the attacker model and who is my attacker if I'm an offensive attacker. In this case, my attacker is the reverse engineer who tries to reverse my precious zero-day exploit. And when it comes to network defenses, also these next-gen or breach detection systems are my attackers, because I really don't want them to analyze my code. And I will also talk about what are the capabilities of the attacker. First of all, the reverse engineer can record and replay the network traffic, right? Reverse engineer can also debug in the browser, for example, at the JavaScript level, if the reverse engineer has access to the document object model in the browser. The reverse engineer can also debug the browser at the assembly level, but not always. For example, if the attacker targets the latest iPhone, in this case, chances are high that you don't have any jailbreak for that iPhone. And if you can't jailbreak your iPhone as a reverse engineer, then you don't have any assembly level access to the iPhone. So assembly level debugging might be possible on Windows, but on mobile platforms, it's not always true. Now, what can a network forensics reveal about an encrypted exploit delivery? You can see on the wire a bunch of crypto libraries, which can do key generation, elliptic curve cryptography, AES, stuff like that, which is pretty common, I would say. You can see the public key exchange itself, and after that, you only see some encrypted blobs on the wire. And if you don't have the shared key, then basically you cannot reverse engineer what's inside, because you cannot break the encryption. Debugging the code in the browser is still possible, but during the presentation I will show you some ways how you can make these tricks harder. So why do I think this is new or this is different? Previously, before this encryption, all exploit code delivery was obfuscated. And sometimes they have used encryption, but they have sent the encryption decryption keys together with the encrypted content. So this is not a real encryption, or what I do really mean that reverse engineers can use this key to decrypt the content, so it's not a real protection. And why do I believe that this is different than SSL or TLS? And how does this affect the exploit replay. So SSL TLS, if you control the client, and whenever you are a reverse engineer, you control the client, then man-in-the-middle attack in a TLS connection is trivial, right? So for example, how many of you guys have used burp? Yeah, so if you use burp, you know how you can intercept SSL or TLS traffic. You just install this burp certificate in your browser, and from now on you can inspect all the traffic. So it's nowadays it's very easy to man-in-the-middle TLS connection if you can control the client. Previously, when reverse engineers tried to analyze exploit code in browsers, they have used a technique called exploit replaying. And I mostly use Fiddler for this exploit replay. I'm not sure if there are any other tools out there to do that. But what's really interesting about the Iron Squirrel-based exploit delivery, that this exploit cannot be replayed, because the client will generate a different public and private key, and the client will send the different public key to the replay server. So now the replay server sends the encrypted data back to the client encrypted with the old key. So the client won't be able to decrypt it, or it cannot generate basically the new keys and fails to replay. Again, I think this was very tough to understand, so again, go back to the demos. So here you can see Fiddler, and I'm going to use this browser and exploit it. In this first request, I'm using a static exploit, so there is nothing fancy here. It's just basic metasploit. And now I am moving this request and response to the Fiddler autoresponder tab. And what's very nice about this autoresponder, that whenever the proxy detects that the client request matches what's already stored in this autoresponder, the proxy will answer. So this is how you can basically replay the attack anytime you want. So if I go back and I use the same URL, the exploit works, and on the left you can see that Fiddler shows with the purple background that this traffic was delivered by Fiddler itself, so it was not a response from the server. Now let's see what happens if I use the encrypted exploit delivery. As you can see, the exploit still works, but if we look at Fiddler, here we see a lot more requests, and it's because I have to send the crypto libraries, I have to do the key exchange, then I have to deliver back the encrypted exploit. And now if I try to use Fiddler to replay this exploit, you can see that nothing happens. And as you can see here, the Fiddler responded with a 404 not found. And the reason for this, because the client sent a different public key to the server. So Fiddler said, this is a new request to me, I have no idea how to handle this. So it just sent back a 404. Of course, we can fine-tune Fiddler, and let's say, all right, you don't have to be that strict. Let's just answer to the client, no matter what kind of public key is sent. But here you can see that still nothing happened. The exploit was not working. Here I have to restart the exploit just to see what happens on the console. And here you can see a JavaScript error called corrupt GCM tag doesn't match, which basically means that the crypto library said, I have no idea how I can handle this encrypted exploit traffic. I don't have the keys to decrypt it. So, how many of you guys are into Archer? Hands up. Okay, so if you do a lot of exploit replay and you really want to mess with the reverse engineers, you can now see how awesome this technique is, because now it means that the reverse engineer has only one chance to analyze the exploit itself. And you can say that it's only me who cannot replay this encrypted exploit traffic, but turns out I'm not the only one. If you check this blog post from Trend Micro, you can see that Trend Micro is also struggling with this kind of encrypted exploit delivery. And it is pretty funny because turned out that the Ostrom exploit kit group, they didn't use this encrypted exploit delivery to hide the exploit code because it was a 0-day. They are hiding it because they are the only group who were able to develop exploit code for this already known and patched vulnerability. And now, because they protect their exploit code, all the other exploit kit groups cannot copy their exploit. So now they are more successful on the market because they are the only one who can exploit it. Now let's talk about defense and offense a little bit. And we'll talk about prevention and detection on the network level, analysis on the endpoint, how to make endpoint analysis harder. First of all, whenever you attack a client, using one-time URLs is your best option, which means the attack URL works only once. If you are in law enforcement and you want to attack all the visitors of the site, this might not work for you. But in this case, what you can do is that you use URL only once per user. So you check for logged-in users and you keep track which kind of users you have already exploited, and you only target them once. And this one-time URL is already implemented in my proof of concept code. You should also use time limits in your code to prevent manual debugging. So for example, there is a 1 minute difference between the first request and the second request. You can be sure that someone is manually debugging it. It is always a good idea to remove the document object model from the browser after your exploit runs. And let's see the tar browser exploit with this encrypted exploit delivery. So here you can see I am visiting the exploit site. And meanwhile, I'm showing you the document object model. And here we can see very long encrypted content. Now the exploit runs, so that's why the browser hangs. And the exploit is finished, and you cannot see anything in document object model anymore. And this is what you can see on the wire. And as you can see, it is basically just very long encrypted content. Now if we try to decode it, as I already shown you in the first demo, you don't get back the original content. And the reason for this because I immediately remove the decryption key from the memory as soon as it's not needed. But if I look at the Wireshark traffic, I can see that the exploit was successful. And the way this exploit works, that it initiates a new network connection to a fixed server, and it will leak the machine name and the MAC address of the machine to this server, and because it's running outside of Tor, it also leaks the original IP address. And as you can see, without the decryption key, there is no way you can decrypt this traffic. Okay, what can you do to prevent against exploits like Iron Squirrel? You can try to detect encryption, or for example, you can try to detect the JavaScript libraries, but this will lead to a lot of false positives. You can try to use domain whitelisting, but again, this is very hard to implement. And last month, I finally found a real solution to this kind of attack, which is called web isolation. And this is a new technique, and there are some vendors out there who are providing this service. And how this really works is that you are not using a web proxy, but this proxy basically is a browser which renders all the content the client browser wants, and it will send the rendered content to the client. So it's a little bit similar to something like remote desktop, but in browsers. It's totally different under the hood, but it actually breaks all this kind of exploit delivery. If you are the attacker, there are many ways how you can improve your attack. For example, if there is domain whitelisting used by the clients, you can use watering hole techniques, or if you are in an NSA or something like this, you can use quantum insert techniques, but I'm not sure that this capability is available for all of you. There are also ways to analyze the Iron Squirrel exploits on the endpoint. You might try to log the shared keys, fix the random generator, somehow hook the GS code. You can use remote debugging for iOS Safari, or this is the best one, you can use a detailed JavaScript execution trace log. And I have a demo for this as well. So there is this awesome project from another Hungarian guy, and it basically hooks, it attaches itself to the browser, and it basically hooks key functions, for example, the eval function and also the document write function. So whenever the exploit code is extracted in the memory, it will log the exploit code itself. And nowadays, this is basically the best chance for reverse engineers to get the exploit code. Again, there are some improvements from the attacker side. What you can do, you might try to detect the debug window. You should always do a proper fingerprinting of the target before you deliver your exploit. You can also use some code obfuscation. You can generate multiple Diffie-Hellman keys and check whether they are the same, because if they are the same, you know that the random generator is fixed. Stuff like that. But you can also add a lot of junk code. And the best way to bypass this debugger-based analysis, if you use other functions than eval or document write. And turns out JavaScript is so flexible that there are like 40 different functions which you can use with the same functionality as eval. So a determined reverse engineer can always restore the exploit from a memory dump, or they can put breakpoints on exploit-related function calls, and that way inspect the memory. But even though this kind of encrypted exploit delivery can delay the analysis or the discovery of the zero-day exploit by days, weeks, or even months. As mentioned, you can also chain your exploit to encrypted malware delivery, which is already implemented in my proof of concept code. And as always, you should do all the anti-stuff whenever you create your own malware. I wanted to integrate this into Metasploit, but turns out it's pretty hard, and I spent significant time with it, and turns out that creating your own Metasploit module is pretty easy, but I basically have to do a heart surgery on Metasploit, and I am not a core Metasploit developer, so I myself cannot do that. If you are a Metasploit developer, hands up. No one? Conclusion is, I think perimeter security is dying due to all the mobile devices used and all the encryption trends, especially if exploits are delivered in an encryption fashion. And in case the attackers used Iron Squirrel for the iOS 0-day, then they could have prevented the leak of the code. The same goes for the Tor browser 0-day. And if attackers deliver encrypted exploits with one-time exploit URLs, it makes reverse engineering a nightmare. And it's very important to note that Iron Squirrel is about bypassing network-level defenses. So it doesn't bypass any endpoint defenses like memory corruption, protection, software like EMET. And whenever you have very expensive browser 0 days, OPSEC is important. There are some ethical dilemmas with my research. For example, why do I help the bad guys? And I always ask, who are the bad guys? Because in my point of view, neither offense nor defense is bad by itself. So for example, whenever the FBI targets pedophiles, I believe that this kind of framework can really help and make the world a better world. And I also do believe in evolution. So if you already know about this attack and you work on the defensive side and you prepare yourself against this kind of attacks, then you are in the better position than all your neighbors. And yeah, that's what all I wanted to share with you. My code is on GitHub. You can clone it, you can use it. It's free, and that's all. Thank you for your attention.
So, are there any questions?
Nice presentation. So why couldn't you do the crypto stuff on other Internet Explorers?
Yeah, I didn't spend too much time on that. The short answer is that I'm using a specific Java crypto library for all the crypto because I really don't want to implement it for myself. And that one is not compatible with IE10 or others. The longer explanation is that everything below IE10 is just crap. So if you remember all these compatibility tests like the ACID test, where you can test with CSS and stuff like that, the score of the browser, everything below everything I10 or below is just get crappy results. So it's so incompatible with any standards that, I mean, it might be possible to re-implement the crypto library to be compatible with older IE, but it will be a real pain. Any other questions?
No more questions? Then thank you again, Sultan.
Thank you.